Hey guys, I'm back. We're going to continue on with some of the work that we've been doing, looking at sources of pointing error and things we might do to reduce the pointing error. And one of the issues I'm going to take a look at in this video is the contribution of the auto-guiding algorithm itself into its ability to deal with various sources of pointing error. Just to review a little bit from last time, in the last video I took a Autoguide log from PhD2, and this is the right ascension data from that night, and broke it down into the frequency domain, converted frequency into period by simply taking the reciprocal. From that we were able to identify various mechanical sources of contributions to the pointing error, and everything below that level I attributed to the atmospheric sources of pointing error. We then rolled up that pointing error and did a cumulative pointing error analysis, which pointed out several things. First of all, that seeing contributes about, I don't know, 70 to 80% of the pointing error, and the mechanical portion is, 30 to 20% of the total pointing error. So there's only so much benefit we're going to get by chasing down the nature of the construction of the mount. The second thing that came out of this analysis was that really the primary contributors to the pointing error are sources of disturbance, whether mechanical or atmospheric, that have a period or periods less than 30 seconds. If it's a mechanical or atmospheric source of disturbance with a period longer than about 30 seconds, well, it turns out that the AutoGuide algorithm handles that just fine. And an example of that are the fundamental second harmonic and 8/3 harmonic characteristics of the Celestron CGM worm gear. Those have periods in the ranging from 170 seconds to 478 seconds, and those are very long comparatively speaking, and are handled just fine, and contribute very little to the total pointing error. So those were some of the things that we observed. Seeing is a big contributor, 70 to 80% for me. PEC training and auto-guiding, particularly auto-guiding, does a great job with disturbances that have periods larger than about 60 seconds, and that certainly takes into account the worm gear and its harmonics. Most of the pointing error is coming from atmospheric and mechanical sources with periods of oscillations that are less than about 30 seconds. And for example, ball bearings, I think, tend to fall into that category on the mechanical side. But one of the things that I commented on, because it seemed like that the auto-guiding algorithm, which is issuing commands, correction commands, every 2 seconds or so, should be doing a better job at correcting sources of error with periods ranging from 10 to 30 seconds. So I was surprised that that didn't seem to be happening, and that's what is leading me to do this little video and do further analysis on this. I want to understand the guiding algorithm and whether or not it is in fact or should be capable of handling sources of disturbance in the 10 to 30 second period range. Here's a picture we're all very familiar with, those of us who are doing auto guiding. This is the PhD2 screen. I'm sure we've all spent far more hours than we'd like to admit staring at this screen, but there is a ton of information in here. First of all, for those of you who are not familiar, this window down in the lower left-hand corner, this is essentially the view of that the guiding camera has through the guide scope. And within this view, the user selects a star, which I have done here, and the guiding algorithm locks onto that star and sends commands to the mount to keep that star located as best it can at the intersection of those two green lines. Okay, over here is a blown up picture of that star. The star is a bright smudge, and part of the objectives of the guiding algorithm is to identify the centroid of that blob, and then to measure the distance from the centroid to the crosshair, where the axes cross. And then that is the pointing error, which we get a real-time plot of during a guiding session up here in the upper plot. Now in this case, this is showing both the right ascension and declination errors. Right ascension is in blue, declination is in red, and the objective of good guiding is to make those lines flat at 0 arc seconds. Right now you're seeing them basically bounce between plus and minus 1 arc second, and I don't know if you can read this on the screen or not, but it says that my pointing error, is on the order of 0.56 arc seconds for both right ascension and declination, which is actually, for me, again, pretty good. All right, but that's what the guiding algorithm is doing, and there are a number of parameters that play into this. First of all, there's the so-called exposure time, which is also the command interval time. In other words, the guiding camera is allowed to observe a star for this period of time, and then at the end of each exposure time interval, the guiding algorithm computes the correction that needs to be sent to the mount to correct for any pointing error. Now, there are a number of parameters that are used to control how the algorithm computes that correction that it sends to the mount, and those of us who play around with this are very familiar with trying to dial in exactly the right recipe of aggressiveness, which I use here is 70% in this case, hysteresis, which is set at 15% here, minimum movement, which is a way of telling the guiding algorithm to ignore any apparent pointing errors that are less than or within, in this case, 0.2 pixels. So it simply ignores them and doesn't issue a command if the measured pointing error is less than that. And then a maximum duration. The guiding commands are in the form of pulses, the pulse in terms of time, pulse width in terms of a time, and in this case I've got the maximum pulse width set to 2000 milliseconds or 2 seconds. And so what we want to do is come up with an algorithm that essentially replicates what the PhD2 algorithm is doing, just so I can study how that algorithm performs with disturbances that have specific periods of oscillation rather than the very complex time history that we get when we actually measure real world performance. This is a picture of pointing errors, a function of time, kind of zoomed in. The dashed line represents now, when a corrective command is going to be issued. It follows a previous command that was a distance and exposure time distance in the past. Obviously, with this curve, we don't have access to the future. All right, so we don't know what the guiding performance is going to be in the future. We only know what it is has been in the past and up to this instant in time. And so we want to determine a proper guiding command for this instant in time. Well, the first thing we do is to take a look at what guiding error we have. All right, in this case, it's the distance from the centroid of the star to the center of the crosshairs that we were just looking at. We'll call that alpha sub error, the error in the right ascension, the pointing error in the right ascension. The first thing we do is check to verify that the error amplitude is greater than the minimum movement setting that we have, which in this case it is. Now, in this previous command increment, we would have looked at the error. It would have been down here, lower than the minimum movement line, and we would have simply ignored this measured error and not have issued a command. Okay, that's what minimum movement is doing. It's telling the guiding algorithm to ignore any measured errors that fall between those two dashed green lines. All right, now once we have the error, the angle error, and we decided we need to it exceeds the minimum movement setting, then we need to issue a command, and it's going to determine the pulse width based on the Autoguide rate that we have set in our mount. This is not a PhD2 setting, it's a setting we put in the mount ourselves, and it's basically usually expressed in terms of a percentage of the sidereal rate. Now, here is a plot, or a kind of a notional plot of the right ascension rate, the angular rate of the right ascension axis about the right ascension axis. Obviously, the right ascension axis is continuing to rotate to compensate for the rotation of the Earth. And the sidereal rate, the tracking rate, if you will, is a sidereal rate of 15 arc seconds per second. Now, I've got shown on here a couple of commands as to what they might look like in this picture, and they are issued, of course, at intervals of the exposure time, as we discussed, that one setting at the bottom of the PhD2 screen. But let's take a closer look at what a command looks like. First of all, the height of the pulse that's being sent is the guide rate that we set in the mount. Okay, for me, again, it's about 50% of the sidereal rate, which is about 7.5 arc seconds per second. So that's the height of the pulse. Now, PhD2 uses this known height that we define, and given the measured angle, whatever pointing error that it's going to compensate for, it simply divides that angular offset, that angular error, by the guide rate speed, and that provides a duration for the pulse width. Okay, and this pulse width has to be less than that maximum pulse width setting that we have on the PhD2 screen. I've got 2,000 microseconds. This is down in this example that I'm showing you here. It looks like it's closer to 600 microseconds. All right, now the problem is this pulse ideally is a nice rectangle, you know, and the area in the pulse, T sub D times the guide rate, is the angle that we're correcting for. In reality, it's a little more complicated because there'll be a period of acceleration where the mount has to accelerate, that is to shift from the tracking sidereal rate up to the tracking rate plus the guide rate, and then it has to decelerate to come back down to the tracking rate, and that deceleration may not be as clean as we assume it is. It could be fairly sloppy. We don't know. I don't know what this actually looks like. For the sake of this conversation, and I suspect from the perspective of the folks who wrote the guiding algorithm, we just assume that it's going to be a rectangle, that it, for all intents and purposes, the acceleration and deceleration periods are small compared to the pulse width, and therefore the area under the pulse, T sub D times the guide rate, is in fact sufficient to compensate for whatever angular rate or offset angle we're trying to compensate for. So let's just make that assumption going forward and talk a little more about where does this pulse width come from. Well, the pulse width is, and I'm guessing a little bit about this, by the way, pulse width is a function of that hysteresis setting that we saw in the PhD2 window, and also the aggressiveness setting. All right, the hysteresis setting is a way of taking into account past history, hysteresis history. Okay, that's what it's doing. A hysteresis setting of 0 basically says, if you look at this little formula I put down here, where H is the hysteresis number, a hysteresis setting of 0 would basically say, take the error that you measure right now and assume that that is the actual error. Now, you might say, well, why wouldn't you do that? Of course, that's the smart thing to do. Yeah, but the error is merely an estimate of what the error actually is, and it doesn't take into account that there is also error in estimating what the error is, because you have to estimate where the centroid of that blob of a star is relative to the where those two green axes cross. So that in of itself has got error associated with it. And sometimes you try to compensate for that error by saying, you know, instead of just giving me this instantaneous view of the error, let me also consider the history. Perhaps it's the average of the last 10 measurements of right ascension error. And that's what hysteresis is doing. It's allowing us to factor in some of that past history. So, for example, if I had a hysteresis of 50%, then I would take the error that I measure right now and multiply that times 0.5, and then add that to, perhaps, the average of the past 10 measured right ascension errors multiplied by 0.5. And so that's a way that we can soften the blow, if you will, of the instantaneous error measurement and try to smooth out. It has an effect of smoothing out the command so that we're not rapidly jumping back and forth and giving commands to the mount. Now, once we take this hysteresis modified error, pointing error, we take that error, all right, and divide it by the guide rate to come up with the effective pulse width. But we don't use that pulse width directly, all right? We modify that by this aggressiveness parameter. Sometimes what you'll find out when you're doing auto guiding is that taking this pulse width and using the full pulse width, you end up overestimating or overcorrecting for the error. All right, and then you'll compute an error to compensate for that error, and you'll overshoot that error, and it becomes a bit of a tail chase where you never quite catch up. So one way to solve that is by decreasing the aggressiveness parameter. Instead of using a 1.0 or a 100%, you use, as I was in that example, 70%. And effectively what that does, it just takes this pulse width that you would compute based on the error and multiplies it times 0.7. And so instead of getting the full pulse width, I might use only 70% of it, or 50% of it, or 10% of it. Now, if you set the aggressiveness parameter to 0, well, you're not going to make any correction at all because you've defined a 0 pulse width to be sent to the mount. So you don't want to do that. But it is one thing that you might be interesting to play with. But anyway, this is how I imagine that the hysteresis and the aggressiveness parameters are being used and being implemented in the PhD2 guiding algorithm. Let's look at what this effect is on a purely periodic signal. So in this case, I've got a 5 arc-second error signal that has a period of 80 seconds. All right, and this is what my right ascension error would look like in the PhD2 window if I did not have any auto guiding turned on. I would simply have a sinusoidal motion as the right ascension swings 5 arc seconds one way, then goes back 5 arc seconds the other way, and then back and forth it goes at a period of about 80 seconds. Now, with auto guiding and using this algorithm as I have just described it, this is the signal we would get. Now, if you look real closely, you'll see that it's kind of choppy, kind of has a sawtooth character to it. The second thing you notice here is that, wow, this algorithm is really doing a pretty good job. Notice that it's not eliminating the error completely, all right? But we have dropped from 5 arc seconds down to about, I don't know, 0.5 arc second, or 0.05 arc seconds. All right, so basically we've cut this down to 0.5 arc seconds. Basically, we've cut this down to about 10%, which is pretty good. All right, we've eliminated 90% of the error. We've still got some error left, and that's kind of an important point. But let's take a close look at these sawtooths. These abrupt drops are when auto guide commands are being sent to the mount. And in this example, the commands are occurring at 2-second intervals. So each one of these sharp decreases corresponds to when a pulse is being sent to the mount to correct for the measured error. Now, the measured error is not the distance from the 0 arc second line up to the red line. The red line is what you would have if you did not have auto guiding turned on. Instead, the error is only what has occurred since the last command was given. What has occurred between the commands. And so in this particular case, in this long period disturbance, long 80 seconds, and I mean long relative to how often the commands are being given. So we're issuing commands at 2 seconds. This is a disturbance that has a 80-second period. And so it turns out in this case, my auto guiding algorithm is able to more or less keep up with the accumulation of error and to compensate for it. So it's in effect, it leaves me with about 10% of the error, but it's getting rid of 90% of that error. That begs the question, though. How does this algorithm work, and how does it perform with sources of disturbance that have shorter periods? Well, here's what I found. I did this simulation with simulating several disturbances with varying periods. All right. The case that we were just looking at was an 80-second period. I had a 2-second time interval. There are 3 curves here. One for a 2-second command interval, exposure time of 2 seconds, an exposure time of 1 second, and an exposure time of 0.5 seconds. All right. So at a period of 80 seconds and a command interval at 2 seconds, you can see that I'm coming in at about 0.2. In other words, I've killed off 90% of the original source of error. Now, there's something else that's obvious here. One, and I have actually noticed this in reality as well, that the faster we can give update commands, the faster that commands are being sent to the mount, the more effective the guiding algorithm is. And I have found this to be true, not always true, but I have often found this to be the case with my mount, that setting that exposure time to a low number is oftentimes beneficial. The second thing that comes through pretty clear is that the algorithm, as I've implemented it here, and based on what we've seen in that previous video, the guiding algorithm does a pretty darn good job with long period sources of pointing error. All right, and what also comes through here, the guiding algorithm is not handling short period pointing errors well. Now, this goes back to that plot that we started this presentation off with, and the one we ended the last presentation with, because it's completely consistent with what we're seeing here. All right, for long periods of disturbances with relatively long periods, greater than 30 seconds at least in the real world data, the guiding algorithm does a great job of keeping those under control, and that certainly includes the worm gear, the second harmonic, and the 8/3 harmonic. All right, those are not significant contributors to pointing error. On the other hand, sources of disturbance that have periods less than 30 seconds are the ones that are most responsible for the pointing error. And what this simulation result is showing is that an algorithm like the one or similar to the one that is implemented in PhD2 is a bit susceptible, all right, is not as efficient at dealing with shorter period disturbances. And in this case, I'm certainly finding that here's 20 seconds, 40 seconds, 60 seconds. I'm not. This is not nearly as effective as the algorithm is at dealing with much longer periods. So I think the simulated results that I have here are basically confirming what I have observed with the analysis of actual guiding results. So what does this mean, and where do we go from here? Well, the PhD2 auto-guiding algorithm is a reactive algorithm. In other words, it has to see the error, measure the error, and then it develops a response to the error. So it's reacting to error that has already developed. All right, and by the time it issues a command to compensate for that error has changed again already. All right, and so for fast changing errors, short period sources of disturbance, it just can't keep up. All right, and that's the main thing here. Reactive algorithms have difficulty keeping up with errors that change quickly, short periods. Short, that is, more or less relative to the rate at which we're giving commands. Now, conversely, and we have observed this is also true, they do a great job with long period sources of error. And that's their principal intent, is to deal with that. Periodic error with the worm gear, perhaps a tracking rate that's a little bit off of the true or the ideal tracking rate. It can deal with long period sources of error, and in fact our analysis from last time confirms that. The problem is that peak seeing disturbance occurs with periods between 15 to 25 seconds. There is a statement out there, a recommendation out there for those who follow auto guiding forums and discussions about auto guiding. Don't chase the seeing. In other words, don't play with the aggressiveness parameter, the hysteresis parameter, or the exposure parameters, trying to capture or follow every single twitchy movement of that blob of a guide star relative to those crosshairs. That's chasing seeing, and you won't be successful, and there's a good reason. This algorithm just can't keep up with those rapid motions that are occurring in the 15 to 25, primarily in the 15 to 25 second range. Now, unfortunately, my mount and some mounts out there have components, probably ball bearings, that rotate with a fairly fast or fairly short period, all right, compared to the worm gear. Worm gear is rotating once every 478 seconds, but that's geared down, and there are ball bearings. Ball bearings have a very small radius compared to the shaft, and so a ball bearing will make many revolutions for a single revolution of the worm gear. So they are a much shorter period element in the mechanical system, and those elements are certainly visible in the frequency domain analysis we were talking about last time. My mount in particular has a fairly significant contributor around the 15-second period mark that is responsible for a good bit of seeing, or a good bit of pointing error. So that's a problem. Now, I have found, and the analysis that I've done here sort of confirms that this algorithm and the real PhD2 algorithm can respond favorably if you use a faster Autoguide command rate, a shorter exposure time. The problem with that is that a shorter exposure time is not necessarily compatible with a dim guide star, because then you lose signal to noise ratio on your guide star. It becomes much more difficult for the algorithm to identify the centroid of that star, and now the error associated with identifying the centroid becomes a driver instead of just trying to deal with the various sources of pointing error that are external to that. But if you can, give it a try, and perhaps you'll be able to get away with a faster Autoguide rate, and perhaps you'll see, as I have, some benefits from doing that. All right, that's all fine and good, but really, if we're going to do better, and I believe we can do a lot better in autoguiding if we alter the algorithm itself. All right, I think we need to consider kind of a dual mode approach where we have both a reactive and a predictive component to the autoguiding algorithm. All right, right now the reactive algorithm just can't keep up with some of the dominant sources of error, particularly those in the mechanical realm that some of our mounts produce. But it should be possible during the course of operation, for example, over a period of time, say after a minute or 2 minutes of operating, the guiding algorithm can take that measured pointing error, convert it into the frequency domain, identify the principal peaks in that frequency domain picture, and then turn that into an appropriate series of sinusoids and commands that can be laid out ahead of time. Okay, in essence, be placed in a predictive mode so that so that the mount is responding to the error as that error is developing. It'll be much more efficient. That way you're not lagging behind the generation of a solution after a problem has been identified. You're solving the problem as you go, which prevents that error and that error rate from building up. I think if we had this predictive component lying on top of the reactive component that could handle whatever's left over, you would have a much more efficient algorithm, and we would recover some of that we would reduce that pointing error down to what seeing, and perhaps a little bit, maybe even compensate for some of the seeing induced error, and we would have a much better performing system. All right, and this is not a radical thought. It's not a radical new idea. It's very similar to noise canceling headphones. Noise canceling headphones have a microphone that listens to the external environment, then it reverses the sign, if you will, on that measured noise, and adds that to what you're listening to, which also includes that same noise. But in effect, the negative noise and the positive noise are canceling out, leaving you with the music you're trying to listen to. They're pretty effective. You know as well as I do that they don't eliminate all of the background noise, but they do a good job of eliminating a good bit of it. It is noticeable. And I think if we have an algorithm, or can adjust our algorithm for auto guiding to be reminiscent of a noise canceling headphone algorithm, we'll be in pretty good shape. I'm going to be doing a little more thinking along these lines to come up, test it out in simulation, using simulations as I have done a little bit here, but including realistic contributions or realistic assessment of the of the seeing, or the atmospheric contribution, the more random contribution, and see if I can come up with an algorithm or a recipe that can effectively implement a reactive and predictive component, and then we'll see where it goes from there. Perhaps I'll come up with a little video to follow up with this, and maybe offer it as a suggestion for some updates to the PhD2 guiding algorithm. Anyway, just wanted to keep you guys up to date with some of the things that I'm thinking about, and I'll talk to you later. Bye.